Thank you. So I would like to maybe not give really an introduction to geometric invariant theory, which is a technical subject, but I would rather like to introduce a few ideas, a few simple ideas that are basic in the GIT program and that will be useful in the GCT program also. So I will mainly follow the ideas that Bernd Stumpfels began to explain this morning, and explain how to use this finite generation of invariant algebras in order to do geometry. So do geometry will be essentially construct quotients. So there's a very general situation when you have a variety parameterizing some objects you're interested in, and there is a group acting, and you want to find a moduli space, which is to monad by the action of the group, so get rid of some extra information that you have introduced in the problem to understand it better. And so when you want to do that algebraically, there are some complicated issues, and so I will discuss a few of these, and GIT gives you some recipe to solve this kind of problem. So I will be very basic about GIT. I will try to explain how it how it comes in the GCT program, what are the main points that connect the two programs, and also discuss some extensions of the result on the finite generation we've seen this morning that are also useful in the GCT context. Okay. So I will begin with a reductive group, so G a reductive group. So as you remember, there are essentially extensions of compact groups that are themselves extensions of generalizations of finite groups. And so we have this result that so let's think geometrically then. So what a way it will not act on some polynomial algebra, but on some variety. So suppose we have X an algebraic variety. The detection of this group. Okay, so the most common situation, so the basic situation, let's say, will be when this is in some vector space over a field of, let's say, the complex numbers to be safe, and this is algebraic variety, so this means this is given by some polynomial equations, so, a set of solutions of some finite number of polynomial equations. And so you want to construct the quotient of X by G. So the main problem, construct. So you're an algebraic geometer, so you want to construct an algebraic variety, or something close to be an algebraic variety. Let's say an algebraic variety. Y, that I would like to do. X mod G, so which parameterizes the G orbits in X. Okay, so of course, if you forget the algebraic structure, if you just give you an orbit space and put a topology on it, but in general it will not be, and it will be far from being an algebraic variety. So here the main constraint is to find this moduli space. You want to think of this as a moduli space parameterizing this object in X, this subvarieties object in X, as itself an algebraic variety. So why is the finite generation important in this context? Because when we have finite generation, then automatically algebraic geometers can construct algebraic varieties. So the thing is, so instead of looking at all the polynomial on the space V, on the vector space V, we will look at the restrictions on X. Okay, so we denote we call that the coordinate ring of X. So it's called this is the image, the space of restrictions, functions that are given by restrictions of polynomials from V to X. So this is the algebra of functions on my variety that are polynomial, restrictions of polynomials. And by the, so I can extend the results of Hilbert and the finite generation, and it follows that if G is reductive, then the invariant algebra itself is finitely generated. This is true for any finitely generated algebra on which G acts. If you take the invariance, you still get finitely generated algebras in this context. The algebra of invariant polynomial functions on X is finitely generated. And so then we have an algebraic variety associated to X. To that will be the notation is spec of this algebra. So what does it mean? Simply that's a cumbersome notation to say something very simple. It's that we write this as it's finitely generated, so we can choose some finitely many generators, F1 to Fn. And as we have seen, in general, there will be some relations between these generators. There is an ideal of relations with a finite basis. Let's call R1 to Rp. Okay, so each one of these is, in fact, a polynomial in the generators, a polynomial relation. Okay. And what is this spec? It is just the variety. You can think of it as inside Cn and the number of generators, given by precisely these polynomial equations. So spec simply means that you can define this without having to choose the system of generators. This is an intrinsic construction, but you can think of these varieties in that way. You have explicit generators, explicit relations, and the relations give you an algebraic variety. This is it. So then, is it a quotient? So I want to think of it as a quotient. So I have a map. I have a quotient map. Phi from X to Y, which is the most natural thing you would like to do. You take upon X and you look at the values of your basis of invariance. Which is obviously a point in Y. And why is that a quotient map? Well, since the F1 to Fn are G invariants, this map will be constant on the G orbits. Okay. So that's what we want to do. When I said that we would like an algebraic variety X, Y, which parameterizing the G orbits, so implicitly I was thinking of a map. I should have a map, an algebraic map from X to Y, which contracts the orbits, and the fibers are exactly the orbits. Okay, orbits. Okay, this would be the ideal situation. And an algebraic variety, a quotient map, and the orbits are precisely the fibers. Okay, the preimage of a point is one orbit exactly, and I parameterize the orbit like that. So here I'm close to that. I have pi is constant on G orbits, so it means that each fiber is a union of orbits, but I would like to have only one orbit. Okay, and of course, as was already noticed this morning, this cannot happen if the orbits are not closed. Okay, so the problem is that pi does not separate G orbit from its closure, let's say. If you have an orbit like that, image orbit is the image of G by point, and something which is in the boundary here. Well, each G-invariant polynomial is constant on the orbits, so we'll take the same value, of course, on the limit point y. Okay, so already we have a serious problem. If we have orbits which are not closed, then this method, starting from the space of the algebra of invariance, does not work. It does not construct an orbit space. So at least, so it's still a good construction. Maybe I could state that as a theorem. So I want to be technical, but I can say that the traditional terminology is that Y is a categorical quotient. I will tell you what it means. So categorical quotient means that you cannot do anything better in this situation. So it means that if you have some other map, phi prime, algebraic map to some y prime, which is constant on G orbits. Okay, so for all such map, all candidate to be a quotient, then there will be some factorization like this. The map will be first this map pi composed by some other map. And this other map, well, loses some information. So this quotient is really the best thing you could do in this context. So the second thing I would like to mention is that my pi separates closed orbits. Okay, so you could have an orbit here which is not closed, so which has another, maybe a closed orbit in this closure. Okay, so by pi they go to the same point. But if you take another closed orbit here, it will go definitely to another point. The pi makes it does not separate orbit closures, but it separates closed orbits. Two closed orbits, different, are mapped to different points.
It's two different questions. So we could try to separate an orbit from its closure, or we could try to separate two different closures of.
Does it separate if you have two orbit closures, they can share a closed orbit?
And if you have another orbit which has O second in its closure, well, it goes to the same point.
If the orbit closures intersect, then they'll map to the same point. If the orbit closures do not intersect, it will separate them.
The fibers are exactly the union of orbits which have a given closed orbit in their closure. That's me. And this very nice property follows, I could mention that, directly from the Reynolds operator that we made this morning. So maybe I should. For the Reynolds operator, there is a slightly different way to see it. So from the algebra of functions to the algebra of invariance. Yeah, more generally, you can take any finitely generated G algebra and map it to its. It will be a map to the ring of invariance with some nice properties. And you can. The reductive groups, you can think of these as those for which any representation is semi-simple. Any representation, okay, reductive means that any representation, so over the complex numbers, is semi-simple, which means that it is a direct sum of irreducible representations. we have a good understanding, and this will be important in all the theory of representations of reductive group. We just have to understand the irreducible ones, and those are parameterized by some combinatorial data. So situation, the theory is very well understood. So from this, we have that we can apply this to R, and we can decompose. There is a direct sum of R into the one part being the subalgebra of invariance, and we have a direct factor R prime, which is the direct sum of all the non-trivial irreducible representations. Okay, so there is a canonical decomposition, sum of non-trivial irreducible representation. We have this canonical decomposition, and what is the Reynolds operator? It is just the projection defined by this decomposition. Okay, so why do I mention that? This point of view is useful because it makes obvious another property of the Reynolds operator, which is that if you take some, let's say S, any subspace of R which is G invariant, okay, so by the same probability of reductive groups, I can decompose it as in exactly the same way. I take the invariance on one side, and on the other side the sum of the non-trivial summons in S. I have this decomposition, and the Reynolds operator, by the very construction, sends S to SG. Okay? Because a priori, so what I just want to stress is that a priori the Reynolds operator would map it to RG, but in fact it goes to SG, which is contained in S. So if you apply the Reynolds operator to some G invariant subspace, you stay in this subspace. Why does it imply the second statement? Because suppose you have, so I call this O prime O second, so two closed orbits, disjoints. Okay, so there are two close subvarieties of my vector space X. Empty intersection. So what I know from Hilbert-Nuchte-Lensatz is that I can find some obvious reason for which the intersection is empty, which is that I can find some. Okay, so let's say that the ideal of O prime is generated by G1, GK. The orbit of O second by H1, HL. So I can find some relation by the Hilbert-Nuchte-Lensatz, sum of GI plus sum of HJ equal 1, which makes obvious the fact that the intersection is empty, because on the intersection I would add all the GIs, all the HJ equal to 0. So I get 1 equals 0. Okay, so this is in the ideal of O prime, this is in the ideal of O second. But then I can apply the Reynolds operator to this sum. So I will write 1 as phi prime, projection of this by the Reynolds operator. This is G invariant, so this is still by the remark I've just made. Inside the ideal and G invariant. And this one is inside the ideal of O second G invariant. Okay? So I find two functions, G invariant, one vanishing on O prime, the other vanishing on O second. And the sum is 1. So this implies that pi really separates I have two functions which take different values of on the two orbits, which exactly mean that pi separates these two orbits. So I have good news and bad news. Pi is the best thing that I can do. It has a nice property, but still we have this problem. Okay. So essentially what GID, geometric theory, invariant theory, tells you is given a variety in a general setting. Well, you will not be able to construct an algebraic quotient. You will have to give up some points. So you'll need to restrict to some subvariety that you want to be as large as possible. And then on these subvarieties, you will be able to do the quotient. And GIT tells you some recipes to do that in the best possible way. So I would just like to make a few remarks in order to understand which is what could be this open subset on which we will have to restrict to have a good quotient. So to have no bit space, to be precise. So there's a fundamental property of algebraic maps. Which is that, so if you take an algebraic map between some, I will not be completely precise, but imagine you have some algebraic map like this, between two irreducible algebraic varieties. Between reducible algebraic varieties. Yeah, then the point is that the fibers are well behaved. So simply there is an open subset here, U, open, in which the fibers have constant dimension. D. And outside this open set, so the fibers will have different dimension, but the point is that the dimension can only become bigger. Y. Picture will be like that. You have some X. So in X you have some fibers, well, maybe not irreducible, but of the same dimension. And somewhere there can be on a closed subset of Y, there can be some fibers which are of bigger dimension. And if you go deeper to some smaller closed subsets, you can have some even bigger, even fibers of even larger dimension.
Can you give examples like take the variety of the determinant or what happens? So we know there we cannot separate all these closures, and what happens on this, what would the open subspace be in this case, or any other example?
Oh.
Concrete examples.
You want concrete examples? Determinant is an example. So,
What would it be?
okay, so let me give you a statement, and then you will have the determinant will be an example. The first statement is apply this to the action. So you have X. Suppose that you have this group acting on X, and so you have the map. You take an element of the group, an element in the variety. You map it to Gx X. But this is an algebraic map. And what is a fiber? So I want to look at a special fiber of a point XX. What is that? This is so what you want is to have Gx equal X. So it's an element of the group such that Gx is equal to X, which is denoted Gx, so the stabilizer of X. this tells you that, so the statement tells you that the stabilizer on some open subset, the stabilizer has constant dimension, and there is a closed subset on which the stabilizer becomes bigger. Okay. You have to think that when you specialize, the stabilizer can only become bigger. So if you think in terms of orbits, this tells you that
Where x is just c and g is c without 0. And then one can draw a picture.
if you let me give the statement, I will give you the example. So that's for stabilizer, but it's maybe better to think of it in terms of orbits. The orbits of a point x, it's essentially the same thing as the quotient of the group by the stabilizer. You divide by the stabilizer, so this tells you that the orbits has constant dimension on some open subset. And the dimension can only become smaller on some can only become smaller. That's typically what happens in this context. So, if you want to see an example, let's think of C star acting on, I don't know, x equal the space of dimension n, acting by scalar multiplication. So what are the orbits? Well, they are just lines. They have a constant dimension, and there is one special orbit, which is the dimension, which is 0. And in this case, well, you can. What does the construction give? Well, nothing. The algebra of invariance is just the algebra of functions. Constant function. So when you apply pi, you go to 1 point. Because every orbit has 0 in its closure. By scaling, you can go to 0. So if you think in terms of invariance, so every invariant map is constant.
But set x point xx is a closed subset of x squared.
Yes.
So you cannot apply it this way. So you cannot say that there is this open subset of x CPS.
Of course, I can apply it and then intersect with the diagonal.
Yes, but it may be an empty intersection.
Sure, but I'm looking to these fibers. The section is not empty, you always have 1. In the stabilizer, stabilizer is never empty. So another instance of this, you can look at this statement, is imagine you have some orbit space. So let's say constant on G orbits. Okay, so this means that any fiber.
So this is not the same y as before, this is a different y. Yeah. Okay.
X is something generic, Y is something.
Okay.
What do you mean? Okay, so here you can observe that since pi is constant on G orbit, any fiber is as an action of G, is preserved by G. Okay, so what we know is that this constant dimension on an open subset So this means that if we want to have an orbit space, so if you want each fiber to have exactly one orbit, then this dimension must be the dimension of the generic orbit, the same one. Orbit space. And dimension. So dimension is V. This is the dimension of the generic fiber. And then the other fibers would be bigger dimension. So if we think that the picture would be that in the fiber we have an orbit plus possibly something in the closure. This is excluded by this little remark. Because we have something in the fiber which is something, an orbit of dimension d. And suppose this orbit is not closed, so we have something in the boundary. Then I have a contradiction, because the other orbits, I know they are a smaller dimension. But possible only, so we can have an orbit space only if the orbits have constant dimension. This tells you that if you want to make a quotient, you have to get rid of all the orbits which are pathological in the sense that the dimension is smaller than the generic one. So an example is the determinant, because the determinant has some stabilizer which is bigger than the stabilizer of a generic polynomial. So up here, the determinant is something we would like to get rid of when we make a quotient.
There you would just get rid of a singular matrix.
Yes, but yeah, so there is some, let me come to some intermediate notions. So we will not exactly get rid of them. So we don't want really to completely get rid of them, but so we will allow to have something weaker than really an orbit space. So the definitions are, so maybe let's take the context. So the theory is what we have for projective varieties, let's say. So we take a projective variety. So the difference is that we are in some projective space, and our variety is given by some still polynomial equations, but which are homogeneous. Homogeneous polynomial equations. And we suppose that we have an action of a reductive group G on X. And this action comes from a linear action on V. Okay, so because we are in this simple situation, we have a representation of G. We look at your projectivization, and inside something which is stabilized by the action of G. Okay, so we can still look at polynomials on V. Then they are no longer functions on X. Okay, they're not exactly functions because of this X is in the projective space. But still we can be interested in that. So no longer functions. But still we are going to use them. So the first definition is that so the point X is said to be semi-stable if so there is some invariant polynomial that does not vanish on this point. Okay, so before giving the second part of the definition, let me make one remark, which is that in this definition there is a kind of interplay between what happens in the projective setting and in the affine setting. So here we have x in P of v, but we can, so given by some polynomial equations, we can look at the polynomial equations and what they define in V itself. Okay, so there is an affine algebraic variety, x star, defined by the same equations. Okay. It's a cone over x, if you wish. Defined by the same equation. Okay, and since I started with an action of G on V, this is also endowed with a G action. Okay, and each time I have a point here, I can choose a non-zero point, which I denote by x star, non-zero, such that x is a point in projective space corresponding to x star. And there is an interplay between the action of G on x star and the action of G on x. So here, if I have here I should have written P of x star. This to really make sense. And so I'm reduced to the previous citation when I look at an affine variety and a set of invariant polynomial on this variety. And so what does mean this condition? It does exactly mean that when I have, remember I have my factorization. Okay, so I have 0 going to 0. And saying that precisely means that x star is not mapped to 0. Okay. And since I proved to you that this quotient map separates the closed orbit, this means that the closure of the orbit of x star does not contain 0. It's exactly equivalent to this. So I have 0, I have x star. I could imagine that I have some points in G making it as close as possible to 0, and this should not happen for semi-stable points.
So somehow you want G to be like SL instead of GL then or something.
Can be defined for reductive group. And it's clear that if I take GLN, so I'll be in trouble.
Okay.
So that's a good remark. If I want to hope for the existence of any semi-stable point, I need that my group does not contain scalars. Okay, so that would be the important point.
So are you imagining a situation where you know the invariant ring and it's easy to find such a certificate that you're semi-stable, or the other way around?
No. Finding the invariance is always too difficult. So I want to try to understand the quotient without computing the invariance.
So somehow you're going to be able to tell whether something is semi-stable without producing.
Yes.
Tells you it is semi-stable.
Try to give you some recipe. So the second thing is that
That works only very special cases.
we need very special cases, but yeah. But
We only study special cases, so it works in case we care about.
what I want to stress, what I will stress in a few minutes, is that the property we really are interested in is that the orbit of the point corresponding to determinants of permanence are closed. So here you see that there is natural condition on the boundaries and the probability of being closed, which appear here. So in fact, that's another definition, which is that X is polystable if semi-stable. We need that, except for 0, and the orbit is closed. Maybe I should make a remark about that and insist on this definition, because so the terminology is not. completely well established. Well, what I should say that there's the fundamental book by Mumford on geometric invariant theory, and the terminology which is used in that book is not the terminology which is used in modern treatments of the theory, so there can be some confusion. Okay, so the most common terminology for this property, Gx star being closed, is polystable. So the last definition is really not Mumford. The point is stable if, so it's a polystable, and the stabilizer is finite. Okay, so most text about GIT you will focus on this notion of stability. The stabilizer is not always supposed to be finite, and this is not always the case in the situation we're interested in. Typically, dominant and permanent have infinite stabilizers.
So why is there semi-stable in the second point?
Just to avoid zero.
X is in the projective
dimension. Okay, so the main theorem of GIT is so if I take there exists a quotient, there exists a categorical quotient. The semi-stable locus. And it restricts to an orbit space on the stable locus. I really want to mention this theorem because that's one of the culminating points of the theory. So it tells you that you can do a quotient. It tells you exactly. Well, there are some subtleties here, but which points you have to keep to be able to make this quotient. And it tells you that you have really an orbit space when you restrict to the stable.
So on polystable points, you're going to...
Polystable, okay. So then you can be more precise and say that precisely what happened on the semi-stable but non-stable locus. And this has very precise things to do with polystability. But I don't want to talk about it. So maybe the last thing I want to mention is that the quotient is in fact projective. Which is something very important in the applications. You get a moduli space. So it tells you that the construction is really good because you want to exclude some points, but it's clear that if you throw away too much points, in the end, you will not get a compact space. GIT gives you, when you start from projective variety, you end with a projective modular space. So it tells you that the construction is very good. Okay. And maybe a little example that we already made this morning. If you look at the adjoint action, so let's xg equal SL2. Depending on SL2, so matrices of trace 0, traceless matrices. You can projectivize the action. Then think about it. So what's Bernd has said this morning, you should see exactly the picture.
So this action is by conjugation?
By conjugation, yes, sure.
You mean the Lie algebra here, right? When you write traces.
The Lie algebra in the agent action. SL2 is the Lie algebra of the group, and it's the space of traceless matrices. So yes, so I can give a few hints about Luke's question. When you want to, so the other example would be to look at.
You're going to tell us what are the semi-stable points here and so on.
And this, that's an exercise that have been done this morning already.
No, but the question, my question is, how is this example? That's more or less what this example is what Bernd was.
Yes, discussed this morning. So you have two invariants. You have one invariant.
I don't quite understand how this example reflects the discussion that we had before. The example per se, we had. How does this reflect the whole analysis that you talked about?
Yes. So.
Connect the two.
Yeah. So remember, you have the null cone, which is the space of nilpotent matrices. Okay. You had the quotient map, which was given by either the determinant or the trace of the square. Pi from SL2 to C, given by taking a matrix M to the square, to the trace of its square. Okay, so this is. So I wanted to mention this example because you have, in this case, you have. So it's a bit too small, but you have, according to Jordan decomposition, you have your matrix is either diagonalizable with a non-zero eigenvalues. Or it can be just to this form, or it's zero. Okay, so geometrically you have so you have zero, of course. Then you have the nilpotent cone, which is in dimension 2, and then you have all the other orbits. Okay, so what you will throw away is this part, and then you have a well-behaved quotient. All the orbits are two-dimensional. So at least in the file setting, you have a quotient given by C star. So you see that what I noticed is that we have to throw away the orbits that don't have the right dimension, but this example tells you that you have to throw away more orbits. Okay, n has a correct dimension, but still you have to.
But here you're acting on traceless matrices, so there's just one invariant. The quotient is a point.
So I wanted to give the example of binary forms briefly. But, okay, so very briefly to answer the questions. So start with C star acting on V. Okay, so in this case we know that the action can be diagonalized. So when you have some so rho of T, so the map rho is given by, in some basis, your matrix will be given by diagonal matrices for some exponents, E1, En, integers. So V has dimension n. Okay, so when you take a point, x star, So you can decompose it into respectively to this with respect to this decomposition. Okay, so some components will have 0. I keep only the ones that are non-zero. And then I get some exponents. The action is like that. Okay, and so it's star. And when you have 0 in the closure, well, of course, when all the exponents are positive. Okay, so 0 is in the closure, exactly.
So D equals E, is DI equals EI, or?
No, so the DIs are some of the EIs, but I kept only the XM, XM which are non-zero. So you can see this, and you can see that if DI, so let's say if D1, put them in some order, and the smallest one is 0. So let's say bigger to like that. So you see that when t goes to 0, I will converge to the point xm. So the orbit is not closed. Then you can say a little more, because the xm is in x, it's a limit point. And then we have an action is
But if they're all negative, it's not a little farther.
xm is this component here.
But if all the DIs are strictly negative, then it's also in the closure.
0? Okay.
All the DI are negative.
Sure.
Yeah. Well, you got if and only if there.
Okay, so if I have this situation they are not all positive and the smallest one is 0, then I have a limit point, which is obviously stabilized by C star. Okay, so here I contradict the semi-stability, and here I contradict the stability, because I have something non-trivial in the stabilizer. Okay, so what you use in practice to decide if a point is stable or unstable is the converse statement, which is the Hilbert-Mumford criterion. Okay, so the remark is that if your group G is typically a group of matrices, so a generic matrices is diagonalizable. Okay, so up to conjugacy, you will cover your group by matrices which are diagonalizable, and then you can, inside this tori, so this sloppy here, you will be able to look at these, typically these examples. So there is a map from C star to your group, which is exactly given by this kind of action. And this is the idea. There's these matrices, they are Zariski dense in G. So if you can understand what happens for all these called one parameter subgroup, that you will control what happens for the whole of G. So this is the Hilbert-Mumford criterion. So you call this DM notation is that then you call it the slope of lambda with respect to the point x. So you have two parts, which is that x is stable if and only if mu x lambda is negative for all lambda, and semi-stable and only if or 0. So what we've seen for the action of C star itself, in fact, controls what happened for the whole group if you look at all the one-parameter subgroups, and you can go in the reverse direction. So in practice, you use this. Okay, so as I mentioned, for the polystability, that's an intermediate property in the Hilbert-Mumford criterion. It does not allow you to decide if a point is polystable. So there is a more refined theory due to Kempf, which can be applied in this setting. So the idea is to look at, so suppose we have, suppose that X is non-semi-stable. So 0 is in the boundary of the orbit of X star. Or suppose even that we have non-polystable. So it works. So suppose you have some points which is in the closure but not in the orbit. Okay, then you can, and this means that you can find some, you have X star, and you can find some one parameter subgroup which maps you in the limit to 1. So the Kemp's theory is very vaguely, is the study of the speed at which lambda goes to y. So you can introduce some tool that can control the speed, and he proves that there is one, when up to some equivalence, there's one parameter subgroup which goes faster than all the other ones. And then the upshot is that it's a bit technical, so sorry?
You say where to go, how you quantify the speed?
Speed. Maybe in private, because it's a bit technical. So there is one lambda, so up to equivalence, maximal speed. Sorry? Up to this equivalence, yes, it's a. And then when you have a one parameter subgroup, well, it defines what is called a parabolic subgroup, because which simply means that you have some subgroup of matrices like that. This is a parabolic subgroup, group of upper triangular matrices by blocks, and this is precisely given by the order of the exponents here. So nothing very deep, but there is a parabolic subgroup, and it is unique. So since it is unique implies preserved by the stabilizer. Stabilizer, if you act it by conjugation, it will give you another parabolic with the same property. So by uniqueness, it's in the normalizer, and the consequence is that parabolic are known to be their own normalizers. So this Gx is contained in the parabolic. So this gives you Kemp's theorem. If Gx is not contained in a parabolic subgroup, then X is polystable. Okay, so in particular, if you have a parabolic subgroup, you have one subspace which is preserved by the stabilizer. So if you can exclude that you have one subspace stabilized by the stabilizers, and automatically your point is polystable. So that's an important property we need for determinants and permanence. It's difficult to see that permanence and determinants that do not distinguish any space of matrices, essentially because the stabilizer is big enough, if you wish. And it implies that they are polystable. The determinant, so seen as a point in the space of the n polynomials in the space of n square variables. Are both polystable. Which is an important point in the GCT problem. Sorry? Thank you, I should be precise for the action. The special linear group in square variables. Thank you.
What about the padded permanent?
Yeah, so the padded permanent, so this is, so remember, perm is notation, so still in V, so you have a matrix X, n by n, so you just keep the block n by m here. It says some X, so take the permanent of M. For m by m matrices, I apply it to Y, and I get a degree n polynomial by multiplying by x11 to the n minus m. This is the padded permanent. This one is obviously not polystable, because you see that x11 and y, they are independent set of variables, but obviously you can get some degeneration to perm my, let's say xnn to the n minus m. So you can take a degeneration of x11 to this one. And obviously this is not in the orbit. This is in the orbit closure, but not in the orbit, because this is polynomial in one less variable. So this is not polystable, but so Ketan proposed a theory of partially stable partially polystable points. So here we can, it is not polystable, but we know exactly why it is not polystable, just because we added more variables. So we can control this, and in the theory of abstractions, when we want to find lower bounds for the determinant vs permanent problem, this is not really an issue. You can essentially do like the permanent, as if the padded permanent was polystable. Unfortunately, I don't have much time to explain that. So the last thing I want to briefly explain is how to extend the finite generation statements to more general non-reductive groups. and explain what it is useful. Finiteness for non-reductive groups. So remember that when G is reductive, R the algebra of finite type, then the algebra of invariance is also finite type. So that's a theorem of Professor Popov that essentially this is characterization of reductive groups. If you have a non-reductive group, you can always find an algebra for which this does not hold. But there is a slightly better situation when we can still hope for positive results. So suppose you have a H non-reductive, but a subgroup of a reductive group, and we are a G algebra of finite type. Not just a H algebra, but a G algebra. Then we can ask, in this restricted situation, is H a finite type? Okay. I want to give you an example where this works. So there is a nice statement which is called the transfer principle. Which is that there is a natural map from the tensor product. So take the algebra of functions on G, tensor by R, and take the invariance of G for the diagonal action. So again, there is a map from R. There's a natural map, which is here I take a function. I have essentially an element. So I map it to, I just evaluate the function on the unit element of G. Okay. So the statement is that this is an isomorphism. And when I have a subgroup of G, there is a direct extension of this statement, which is that you can put H invariance on both sides. Okay. So this is nice because you replace the problem of taking a H invariance into the problem of taking G invariance. Something which is bigger. But the consequence is that
C of G, H invariance is finitely generated?
Yeah, so that's the problem. It's not always true. Consequence, if precisely the algebra of invariance is finitely generated, then I can conclude that H invariance in R are finitely generated. When can this be true? So C of G H, so this is the algebra of functions on the quotients by H. So when is it finitely generated? Certainly not always. This quotient can be can have very different types of algebraic varieties. We can have projective varieties. We can have affine varieties. So, for example, if G mod H is affine, okay, if G mod H is affine, affine variety are precisely those which are given by finitely generated algebra functions. So we could apply this theorem. In fact, we have nothing new because this is known to be equivalent to the fact that H itself is reductive. So nothing new. But we can ask that G mod H be close to be affine. You could ask that. So the best situation would be that G mod H would be a subset of an affine variety. It could be Z. And very close to it, which means that the codimension of the complement is at least 2. So we have this affine variety, and we get rid of small subsets, and we get this this orbit. Then the same conclusion holds, because sorry for. We have to change Z a little bit, but we will get that the space of functions on G mod H will be the algebra of functions of the normalization of Z.
Can G mod H be projected?
In some situation, it is projective, yeah. But if it is projective, you don't get any invariant, or you get nothing interesting. Yeah, it's very close to be affine, so very far from being projective. Okay, so, and the normalization is affine. It's a classical theorem. So in this case, you have the statement.
What is this Z to the exponent? I can't read it.
No, normalization.
Normalization of Z. So Klim's question was, is if H is parabolic? So
if H is parabolic, the variety is projective, and you don't get any invariant. Okay, so this was so think, for example, so when do we have this situation where G mod H is contained in Z affine? So you could think it's a bit artificial hypothesis, but if you have any stabilizer, so suppose G acts on a vector space V, because you have a linear action, and you can take any stabilizer. G mod Gx is the orbit of X, so it's contained in the closure, which is affine. The question is, when is the boundary of codimension at least 2? Well, for example, you could take D equals C2 with the action of SL2. You can take X to be this vector 1, 0. Okay. Well, by the action of SL2, you can send this vector to any vector except 0. C2 minus 0. We are precisely in this nice situation where the boundary, which is just 0, is codimension at least 2. So this works. The stabilizer is what is the space of matrices of this kind, usually denoted U. So we deduce that, look at the mod H is space of invariant and the space of polynomials in 2 variables. R. What SL2? So we've proved that. So that's a finite generation statement for non-reductive groups. So if you take R any irreducible representation, so binary forms, you've proved that this is the algebra of covariance algebra. And so this is finitely generated. So this is a very ancient theorem. It is due to Roberts around 1871, I think. The algebra of covariant algebras of binary forms is finitely generated. But the idea can be applied in a much more general setting. So just say very briefly, and I will stop with that. In what context I would like to apply it. So suppose V is Cn. Again, G will be SLN. And take W to be so Cn plus wedge 2 of Cn, etc. And take the direct sum of the wedge powers. I will take my point X to be E1 plus E1 wedge E2. I choose a basis. I take a sum of decomposable tensors like this. Well, so it's just an exercise to check that the stabilizer is again this group of upper triangular matrices with one on diagonals. Thank you. And again, and two holes. See how G mod U is finitely generated. Okay, so you can apply this to get to control some other algebras of covariance. So maybe first we can say that what is exactly this algebra? We have the Peterweil's theorem, which is really an exercise which tells you that C of G is the sum over all the irreducible representations of V star tensor V. When you go to quotient map, you just keep the invariance. Oh, sorry, I'm out of time, so I'm being a little too quick here, but this is just one-dimensional. So for those who know a bit about representation theory, this is just one-dimensional. And there is an action of T, which is given by the highest weight of the representation. It's aligned with an action of C star. And this algebra is essentially the sum of all the irreducible representations. So we know this is finitely generated. So application, let's take 3 copies of it. Let's call this A maybe. So we look at A tensor A tensor A. This is the sum of, so A is the sum of, so I wrote it like this, but as I mentioned, the V's, the reducibles, they are really parameterized by combinatorial data, which are the highest weight. The sum of lambda, where lambda are all the possible highest weight, tensor sum of V mu, tensor sum of V nu. Okay, so I can put duals, it does not change anything. Okay, so I can take the invariance now in these triples. GLN.
The duals star.
Yeah, take the diagonal action of GLN. A is the sum over all representations. I can dualize, it's just an involution. Okay, so I get this. So A is finitely generated, so this triple product is. I take the invariant of GLN, so I still get something finitely generated. It's finitely generated. And when do I have something here? Less than 0, exactly, if and only if V nu is contained in the tensor product of V lambda tensor V mu. So there's something which is usually denoted the Littlewood-Richardson code, or GLN, or SLN. Set of triples lambda mu nu, such that nu V nu is contained in the product of V lambda and V mu. So this is the weight, the set of weights of this finitely generated algebra. So since it is an algebra, when I take the weights, I get a semigroup. Since the algebra is a finite type, I get a semigroup which is finitely generated, so finite type. So this nice statement due to Briand and Knoop that the space of weights is a semigroup of finite type, so that's really a generalization of this theorem by Roberts, and you can apply it in more general situations, for example, for chronicle coefficients.
You speak on Wednesday? No, I speak on Thursday.